Alright, so for this part 2 of the Doppler effect, we're going to be looking at some key extension ideas. This will be useful for obviously anyone doing level 3 to get a higher level understanding, but also this will be useful for people that are doing scholarship. So just a reminder, in this case we are dealing with a moving source, in this case it's a car, and it's moving towards a person. Obviously the guy's name is Timmy, and the car recedes from Timmy, again moving at 15 meters per second and still producing a frequency of 440 hertz. So on approach it produces 440 hertz and then it continues that constant frequency when it's receding. Okay, just a rough estimate, we can say that the change in frequency that Timmy hears when the car is approaching will probably be something like 460 hertz, right? This is a rough estimate. Obviously we have no other numbers, so it'll be a approximation, okay? And then once it's receding, the change in frequency that Timmy will observe would be something like 420 hertz. Right? And again, this should be an approximation, okay? So the key idea is that when the source is approaching, the observed frequency of Timmy is going to be higher than the source, and then when the source is receding away from Timmy, the observed frequency is going to be lower than the source, okay? Now, what we can do is we can graph this change in frequency, okay? So let's say we have a graph like so, okay? And on our y-axis, we have frequency, and this is going to be our observed frequency, all right? And that's obviously going to be in hertz, okay? And on this side, we can have time, right? T, and it's measured in seconds. Now, if we take this middle line right here as where our observer is standing, our observed frequency is going to look something like this, okay? Where the frequency over here is 460 hertz. The frequency over here is 420 hertz, and this middle frequency over here is 440 hertz. So that is the true frequency, right? Or the source frequency, if you will. So you can see here on approach, because the source is moving at a constant velocity, we have a constant Doppler shift of 460 as it's approaching. As we previously stated, this line is where Timmy is standing, and we can see a sudden drop in the observed frequency. And then as the car moves away at a constant velocity, we have a constant observed frequency of 420, okay? Now, one thing I want to point out about this graph is it's not very accurate. The reason for that is because this only occurs when the source moves straight through the observer. Now, in this case, we have a car and a person, and if that source, aka the car, moves straight through the person's gonna die. And so in real life, when you observe the Doppler effect, you obviously don't get run over. So that is the first extension idea I want to discuss, is when we have our observer, right? And the car is some way away, so some arbitrary distance away from the observer, okay? And the car is again moving this way at a constant velocity. In terms of the wavefronts that are observed, it's going to be the ones that are in the direction of our observer, not the ones that are bunched up in front, okay? And so we got to think of those wavefronts sort of coming in at an angle, and then we need to take that angle into account in our calculations. Now, it's only when the car is directly in front and in line with our observer when the wavefronts hit it, and these wavefronts are the true wavelength, and therefore we observe the true frequency of 440 hertz. And then obviously when the car is receding again, we observed spread out wavelengths, and again we need to take that angle into account, okay? And so how do we take that angle into account, okay? And so this next part is going to be more so for the people taking scholarship. However, I think it's still nice to know if you're taking level 3, but this knowledge is not required for level 3, so if you don't understand it and you're only taking level 3, you're fine, okay? So again, we have our car here, okay? And then we have our observer. This car is moving this way, okay? Its velocity, the velocity of the source, and we can split this up into two components, right? So we will have a component coming up this way and a component coming down this way, okay? And we will have a right angle over here, okay? And this angle we can call theta. And so therefore, this velocity component is Vs cos theta, and this will obviously be Vs sine theta. Okay, and if you're struggling to visualize that, remember we have our vector triangles. This can be moved over here, and so we get this, okay, and this is obviously our theta, and then this can be moved up here, and then this right here is a right angle, and so this is our hypotenuse, and so therefore this is cos, and this is sine theta, theta. Okay, there we go. And so if we want to take this into account, when we have our Doppler equation, plus or minus Vs, okay? Rather than just taking the source velocity, we would plug in Vs cos theta into this equation. And so that's how we would get our observed frequency when the observer is not directly in line with the source, Okay, now if we were to graph this scenario, let's say we have our Timmy, okay, and we have this blue car, and this blue car is again not in line with Timmy, but it's not that far away, okay? And so in this scenario, with the blue scenario, the graph is going to look more or less something like a curve, okay? Like so. So it's curved because we're dealing with velocity components, but it still goes through 440 because at some point the car is going to be directly in line with Timmy, and therefore Timmy would observe 440. However, if the car is much further away from Timmy, okay, we are going to observe more or less a straight line, okay, like so. And that line should still go through 440, okay? So the further out we get, the more of a straight line our graph is going to be, the more linear our change in frequency is going to be perceived. So now that's our first idea. Our next idea, I want to talk about circular motion and the Doppler effect, okay? So if we look at a bird's eye view, okay, a bird's eye view of our situation, and let's say we have a merry-go-round type thing, okay? And we have our source over here, and we have, again, Timmy, but this is a bird's eye view, so obviously he's not going to be a stick figure, okay? And this source produces a frequency, again, of 440 hertz, let's say, and we can draw this source at different scenarios, okay? So in this scenario, our velocity component is in this direction, velocity component in this direction, and in this scenario, our velocity component is going to be in this direction, and over here, our velocity component is going to be in this direction. Now, as you can see in this first scenario, our velocity component is pointing directly towards our observer, right? Like so. And so at this instant is when we're going to hear the highest frequency, because this is equivalent to us approaching, okay? And as you can see here, in this scenario, our velocity component is directly moving away. So that's not the straightest of lines, but you get the idea. The velocity component is moving directly away from our observer, and so that's the equivalent of our receding situation, okay? In these two scenarios, we will observe no Doppler shift, okay? And the reason for that is because the wavelength that our observer observes is the true wavelength, okay? And that's because our velocity component is not in the direction of our observer, okay? And if we were to think about this, as this source goes around in a circle, we're going to hear a high frequency here, a true frequency here, low frequency here, true frequency here, high, true, low, true. Okay, and so we can graph this as a sinusoid. If we have our time over here and our observed frequency over here, we can see in this case, we start high, we go low, we go like this. So we start high, then we come down to the true over here, then we go low, and then we go to our true, which is over here, and then we go high again, true, low, true, and then high. Okay, this usually comes up in NCEA as, like, let's say we would have a person, let's say Timmy again, and he is holding a string with a buzzer like on the end of the string, and he's like whipping it around his head, like so. And then there's an observer, let's say to his right, and as basically the question is, what does the observer hear at different points? Okay, and you can say at this point it would hear the high frequency, low frequency, and then true, okay? Those types of questions do come up in the exam quite frequently, okay? Now the last idea I want to look at is that in level 3 we usually deal with a moving source, okay? However, in Skull, we might come across a situation where we have a moving observer. Now, the Doppler equation for a moving observer is as so, okay? Alright, so now I'm going to show you how this equation gets derived. The key idea of the Doppler equation for the moving observer is that there is a relative velocity between the observer and the velocity of the wave emitted by the source. Okay, so if we have a source here, and it's emitting wavefronts, right? These should be evenly spaced, alright, remember? And we have a source moving towards it. Okay, there is going to be a relative velocity in this case, okay? Just imagine a case where we have a car, and this car is moving at 50 kilometers an hour, right? 50 kilometers an hour, and we have another car, okay, moving at 100 kilometers an hour. From this car's perspective, let's call this car 1 and car 2. From car 1's perspective, car 2 is moving at 150 kilometers an hour, okay? That is due to relative velocity. Relative to car 1, car 2 is moving at 150 kilometers an hour. And so if these waves are moving at 340 meters per second, but the observer is, let's say, running at these wavefronts at, let's say, 2 meters per second, then relative to the observer, these wavefronts are moving at 342 meters per second, okay? And so we need to take that into account. Now that is when the observer is moving towards the source. When the observer is moving away from the source, okay, again at let's say 2 meters per second, and we have our source emitting wavefronts, once more, and these wavefronts are again moving at 340 meters per second, so the speed of sound, okay? Then the relative velocity between the observer and the wavefronts is 338 meters per second. And so we can say that when we are moving towards the source, our relative velocity is equal to the velocity of the wave plus the velocity of the observer. However, when we're moving away from source, our relative velocity is equal to the velocity of the wave minus the velocity of the observer. And so therefore we can make a general formula saying that the relative velocity is equal to the velocity of the wave plus or minus the velocity of the observer. Now, our observed frequency is going to be the relative velocity all over the true wavelength. And we know that the wavelength is equal to the velocity of the wave all over the source frequency. Okay, source frequency. And so therefore we can make that substitution. And so therefore our observed frequency is the relative velocity times the source frequency all over the wave speed. And so therefore our observed frequency is the source frequency times the relative velocity all over the wave speed. And then we can substitute our relative velocity for this equation, and we get our observed frequency is equal to the source frequency times our wave speed plus or minus the velocity of the observer all over the velocity of the wave. And as you can see, that is the equation that we have up here, except this should be plus or minus, all right? So now let's see which one has a greater Doppler shift. Let's say for this, our source velocity is going to be 10 meters per second. And let's say in this case, our observer is going to be moving at 10 meters per second. And let's say our source frequency in both cases is going to be 200 hertz, okay? And our wave speed, let's say, is 340 meters per second. And let's say in this case, the source is moving towards the observer, and in this case, our observer is moving towards the source, okay? And so let's now calculate our Doppler shift. First, for the moving observer, we are going to have 200 times our wave speed plus the velocity of our observer, which is 10 meters per second, all over our wave speed. Okay, this gives us an observed frequency of 205.88 hertz. Okay, now for our moving source, we have our observed frequency is equal to 200 times 340 all over 340 minus 10. And this gives us an observed frequency of 206.06 hertz. And so therefore we can see that when we have a moving source, this is when we have the greatest Doppler shift. All right, so that's it for our Doppler effect in level 3. See you.